In episode 76, titled Non-Wi-Fi Options, BLE, NFC, LoRaWAN, and Where They Fit, the focus is on alternative radios as tools that solve specific constraints rather than as competitors trying to replace Wi-Fi everywhere. In network architecture scenarios, these technologies show up as hints that the problem is not get a laptop online, but something more constrained, such as low-power sensors, identity taps, or long-range telemetry. The exam tests this because choosing the wrong radio technology can lead to wasted effort, poor battery life, or security gaps, and because these terms are often used in questions as shorthand for range and power trade-offs. The key decision is rarely about raw speed, because these options exist precisely when speed is not the primary requirement. Instead, you are balancing range, power consumption, bandwidth needs, and the security model that fits the device and environment. When you can map each technology to its typical strength, you can infer the right fit quickly from the scenario details. This episode builds a decision pattern that treats each radio as a specialized tool in the connectivity toolbox. The goal is to help you pick the right tool based on constraints rather than on familiarity. Before we continue, a quick note: this audio course is a companion to the CloudNetX books. The first book is about the exam and provides detailed information on how to pass it best. The second book is a Kindle-only ebook that contains 1,000 flashcards that can be used on your mobile device or Kindle. Check them both out at cyberauthor.me in the Bare Metal Study Guide series. Bluetooth Low Energy, commonly called BLE, is designed for short-range, low-power device communication, and it fits environments where devices need to communicate for brief bursts while preserving battery life. The low-energy design emphasizes minimizing power draw, which makes it suitable for wearable devices, small sensors, and accessories that must run for long periods on small batteries. BLE is typically used for proximity communication, device discovery, and periodic data exchanges rather than continuous high-throughput networking. It also supports patterns like broadcasting small data packets to nearby receivers, which is common in asset tracking tags and beacon systems. The exam often uses BLE to signal that the device is close to a phone, tablet, or gateway and needs a power-efficient link, not a high-bandwidth connection. Because BLE is short-range, it reduces the chance of long-range eavesdropping compared to stronger long-range radios, but it does not eliminate the need for authentication and encryption. BLE deployments often involve many devices, which means operational management, pairing processes, and lifecycle tracking become important. When you see BLE in a scenario, you should think nearby, low power, bursty communication rather than general network access. Near-field communication, commonly called NFC, is designed for very short-range identity taps and quick pairing, and its defining characteristic is that it requires physical proximity. NFC works at distances that are typically a few centimeters, which makes it useful for access control badges, secure tap-to-pay transactions, and rapid device pairing where you want a deliberate physical action. That short range provides a natural control because it is hard to interact accidentally, and it supports user experience patterns like tapping a card or phone to a reader. The exam often uses NFC as a hint that the scenario involves identity verification, access control, or secure pairing rather than general connectivity. NFC is not a transport for sustained telemetry. It is a trigger and exchange mechanism that supports small data transfers and identity assertions. Its security posture depends on how it is implemented, including whether the system uses strong cryptographic authentication and whether the reader infrastructure is trusted and monitored. NFC also fits well in environments where you want to avoid battery-heavy radios because an NFC tag can be passive and powered by the reader's field. When you see NFC, you should think intentional physical tap, identity or pairing, minimal data, rather than wireless networking. Long-range, wide-area network, often abbreviated as LoRaWAN, is designed for long-range, low-bandwidth sensor telemetry, prioritizing distance and power efficiency over throughput. LoRaWAN is commonly used for sensors that send small amounts of data periodically, such as temperature readings, water levels, utility metering, and environmental monitoring. The value is that a device can transmit from far away, often across a large property or rural area, while consuming very little power, enabling multi-year battery life in many cases. The trade-off is low bandwidth and higher latency compared to Wi-Fi and cellular, which means LoRaWAN is not suitable for interactive applications or high data flows. The exam uses LoRaWAN as a hint that the environment involves remote sensors, wide coverage areas, and minimal data payloads, often with devices that are difficult to service frequently. LoRaWAN also introduces gateway infrastructure because sensor traffic is collected by gateways that connect back into the network, making gateway placement and backhaul reliability part of the design. Security is still essential, because telemetry can be sensitive and device control commands can be dangerous if spoofed, so identity and encryption must be part of the model. When you see LoRaWAN, you should think far, low data, long battery life, rather than high-speed connectivity. Selecting among these technologies should be driven by range, power, bandwidth, and security needs, because those are the constraints that define the problem space. Range answers how far devices must communicate, whether the requirement is centimeters, meters, or kilometers. Power answers whether devices must run for years on batteries or can be powered continuously, which influences whether a high-energy radio is acceptable. Bandwidth answers how much data must move and how frequently, distinguishing tiny telemetry messages from continuous media streams. Security needs answer how identity is established, how data is protected, and how unauthorized access is prevented, especially when devices have limited compute capability. The exam expects you to apply this constraint-based selection logic rather than to choose based on brand recognition. A device that needs low power and short range often fits BLE. A device that needs deliberate identity taps fits NFC, and a device that needs long-range periodic telemetry fits LoRaWAN. When you structure your decision around constraints, the correct fit becomes clear even in unfamiliar scenarios. This is the pattern the exam rewards because it mirrors real engineering decisions. Typical use cases help you recognize these technologies quickly in scenario language, including asset tracking, badges, payments, and sensors. Asset tracking often points toward BLE beacons or tags because they can advertise presence to nearby receivers while preserving battery life. Badges and secure entry systems often point toward NFC because tap-based identity is a common pattern for doors and controlled spaces. Payments and point-of-sale identity also commonly use NFC because it supports quick, deliberate transactions and is integrated into many mobile devices. Sensors that report small values over long distances often point toward LoRaWAN because it enables wide coverage with low power consumption. The exam uses these use case words as hints, sometimes without naming the technology directly, so recognizing the mapping helps you infer the right option. It also helps you avoid forcing Wi-Fi into a role it does not fit, such as expecting a battery-powered sensor to maintain a continuous Wi-Fi connection. Use cases are not rules, but they are strong indicators when combined with constraints like distance and battery requirements. When you can map use case language to radio choice, You demonstrate applied understanding. A scenario: choosing LoRaWAN for remote sensors on a large property is a classic fit because the core constraints align with LoRaWAN's strengths. Remote sensors might be placed across fields, along fences, or at distant equipment sites where running power and wired connectivity is costly. These sensors may only need to send small telemetry values periodically, such as moisture levels or equipment status, and they may need to run for long periods without battery changes. LoRaWAN supports this by enabling long-range transmission to a gateway, reducing the need for dense infrastructure. The gateway then connects to the broader network, allowing central systems to collect and analyze the telemetry. The exam expects you to choose LoRaWAN in this kind of scenario because it matches the low bandwidth, long range, low power profile. The key is that the requirement is not interactive user access, but periodic reporting, and LoRaWAN is optimized for exactly that. When you see large property and remote sensors, LoRaWAN is often the intended answer. A common pitfall is assuming these technologies replace Wi-Fi for general access, which misreads their design purpose and leads to poor outcomes. BLE is not intended to provide full network access for laptops and phones, and its throughput and connection model are not designed for general browsing or enterprise applications. NFC is not a continuous connectivity medium, and it is fundamentally a proximity interaction tool for identity and pairing. LoRaWAN is too low bandwidth and too high latency for general connectivity, and it is designed for small telemetry messages rather than interactive sessions. The exam tests this pitfall because it checks whether you understand each technology's constraints and intended use, not just its name. Trying to use these radios for general access often results in frustrated users, complex gateways, and security gaps because the protocols and device ecosystems are not built for that role. Wi-Fi remains the general access technology in most enterprise environments because it provides the throughput and session model user devices need. Alternative radios complement Wi-Fi by handling specialized device communication patterns. When you keep that division clear, you choose the right tool for the job. Another pitfall is ignoring identity and encryption requirements for device telemetry, which can create quiet security risk because sensor data and commands can be abused. Telemetry can reveal operational patterns, locations, and sensitive environmental information, and in some cases, it can be tied to safety-critical systems. If identity is weak, attackers can spoof devices, inject false readings, or send commands that change device behavior if the system supports downlink control. Encryption is important because even low bandwidth data can be valuable, and interception can lead to privacy and operational risks. The exam expects you to recognize that IoT communications need strong identity, secure key management, and monitoring, even when the data payload seems small. These technologies can have constrained devices, which means security must be designed to fit, not assumed away. Gateways also become critical trust points because they bridge device radio networks into enterprise networks, so gateway security and monitoring are essential. When you include identity and encryption in your reasoning, you show that connectivity choices include security posture, not just radio physics. This is especially important in large deployments where device count amplifies the impact of weak security. Quick wins include segmenting IoT networks and monitoring gateway traffic, because gateways and device networks should not share the same trust zone as user devices. Segmenting means placing device traffic into dedicated VLANs or network segments with restricted access to internal resources, limiting lateral movement if a device or gateway is compromised. Monitoring gateway traffic provides visibility into what devices are communicating, whether traffic patterns change unexpectedly, and whether unusual volumes or destinations indicate compromise. Gateways often become choke points where you can enforce policy and collect logs, making them high leverage for security and operations. The exam rewards these quick wins because they show practical governance. You treat IoT as a different risk category, and you build controls accordingly. Monitoring also supports troubleshooting because it helps confirm whether sensors are reporting reliably and whether coverage and gateway placement are adequate. Segmentation reduces blast radius and keeps device compromises from becoming enterprise compromises. When you pair segmentation with monitoring, alternative radio deployments become more trustworthy and manageable. Operationally, documenting device ownership and lifecycle processes matters because IoT deployments often involve many devices with long lifetimes, changing responsibilities, and inconsistent maintenance practices. Ownership means knowing which team is responsible for the device, who approves its deployment, and who responds when it fails or behaves suspiciously. Lifecycle processes include onboarding, credential provisioning, firmware update expectations, decommissioning, and replacement procedures. Without lifecycle discipline, devices accumulate with unknown purpose and unknown security posture, creating long-term risk and support burden. The exam expects you to recognize that managing I/O is as much about process as about radio selection, because unmanaged devices become blind spots. Documentation also helps with compliance because you can show inventory and control of devices that collect data or affect physical processes. Clear ownership reduces the chance that devices remain unpatched, misconfigured, or forgotten after a project ends. When you include life cycle in your design thinking, you show maturity beyond simply choosing a radio. A useful memory anchor is range and power drive choice more than speed because it captures why these technologies exist. BLE is chosen when you need short range and low power. NFC is chosen when you need extremely short range identity or pairing, and LoRaWAN is chosen when you need long range with low bandwidth telemetry and long battery life. Speed is not the primary differentiator here because these radios are optimized for constraints rather than for maximum throughput. This anchor helps you avoid the pitfall of treating them as Wi-Fi alternatives and instead positions them as specialized tools. It also helps you answer exam questions quickly because many scenarios provide range and power hints explicitly. When a scenario mentions multi-year battery life, long-range coverage, or tap-based identity, the anchor points you toward the correct option. When you apply the anchor, you choose technologies that fit the physical reality of the devices. That alignment is what the exam expects. To apply the concepts, imagine being asked to match 3 devices to BLE, NFC, or LoRaWAN and focus on the constraint that dominates each device's needs. A wearable asset tag that must broadcast its presence to nearby receivers while preserving battery life aligns with BLE because short-range proximity and low power are the core needs. A door badge or payment tap aligns with NFC because the requirement is deliberate close-range identity exchange and quick pairing with minimal data. A remote soil sensor or utility meter that sends small readings from far away aligns with LoRaWAN because range and long battery life dominate while bandwidth needs are minimal. The exam expects you to justify the mapping based on range, power, and bandwidth rather than on vague statements about wireless. You also consider security needs in each case, ensuring that identity and encryption are appropriate for the device and the risk. When you can map device constraints to the right radio, you demonstrate the intended decision pattern. This mapping exercise reflects how the exam will often present these terms as scenario hints. To close episode 76, titled Non-Wi-Fi Options, BLE, NFC, LoRaWAN, and Where They Fit, the key is to treat alternative radios as specialized tools chosen to satisfy constraints that Wi-Fi does not address efficiently. BLE supports short-range, low-power device communication for proximity and asset tracking patterns. NFC supports very short-range identity taps and quick pairing for badges and payments, where deliberate physical proximity is the control. LoRaWAN supports long-range, low-bandwidth telemetry for remote sensors that must run for long periods on minimal power. The correct selection is driven by range, power, bandwidth, and security needs, with range and power often dominating more than speed. The most common mistakes are assuming these technologies can replace Wi-Fi for general access and ignoring identity and encryption requirements for telemetry and gateways. Quick wins like IoT segmentation and gateway monitoring improve security and operational confidence, while ownership and lifecycle documentation prevent unmanaged device sprawl. The memory anchor that range and power drive choice helps you interpret scenario hints quickly and correctly. Your rehearsal assignment is a mapping drill where you take 3 device descriptions and state which radio fits and why, because that drill is how you demonstrate non-Wi-Fi selection reasoning the way the exam expects. Thanks for listening. For more audio courses, daily newsletters, and more, please visit baremetalcyber.com.